So good morning and welcome back to the second lecture regarding Laplace transform. This is a little bit lengthy lecture because I have to cover a little bit of ground in the Laplace transform module. So like what we have seen in the properties of Fourier transform, just like that we have properties for Laplace transform also. So if I have in detail given the properties of Fourier transform, including the derivations of each and every property. So there is only one difference between Fourier transform and Laplace transform. Instead of j omega we have s here, that's all. So I need not go in detail about the proof and derivations of all the properties. I just mentioned that and go. So the first one is the linearity property. That is, if of course you know what is linearity property. If x1 Laplace transform x1 of t leads to x1 of s and Laplace transform x2 of t leads to x2 of s, then Laplace transform of the combination of the superimposed signal, that is ax1 of t plus bx2 of t will be ax1 of x plus b2 x2 of x. So very easy to prove. And one more thing, proofs are not necessary with respect to the examination point of view. So you just understand so we rather apply these properties often in all the problems. So that is okay. So problem point of view, these are very important. Then time shift. So this is another very important property. If x of t Laplace transform leads to x1 x of s, then if I delay that signal x of t by t naught seconds or shift the signal by t naught seconds, then Laplace transform of such a signal will be e raised to minus s t naught x of s. So x of s is actually the Laplace transform of x of t, and that x of s will be multiplied by e raised to minus s t naught. That is the Laplace transform of x of t minus t naught. I stress this property because we have to this property is often used in problems. So if we have a signal shifted by t naught seconds, then what is the Laplace transform? The Laplace transform of x of t, that is x of s, is being multiplied by e raised to minus s t naught, where t naught is the shifted time seconds. Then time reversal. This is very easy to understand. If x of t leads to x of s, then x of minus t will obviously lead to x of minus s. Then transform derivative property. This is another property which I'll go in detail, including the proof, because the next two properties we often use while we solve the differential equations. So if x of t leads to x of s, then the first order derivative of x of t, and if you find the Laplace transform of such a signal, that is Laplace transform of d by dt of x of t, then that will be s into x of s minus x of 0 minus. 0 minus is nothing but 0 has 2 points, that is 0 minus and 0 plus. So 0 minus actually represents the starting point of 0 and doesn't have much significance in calculation. So while we calculate, we take 0 minus and 0 plus as same. But 0 minus here represent the initial value. So that is x of s minus x of 0 minus. So proof. So we substitute the signal. So here instead of x of t we have the signal d by dt of x of t. We are finding the Laplace transform. We apply that in the definition of Laplace transform, but purposefully we have taken integration from 0 to infinity rather than integration from minus infinity to infinity, which has its own reasons, which we'll understand when we come down the derivation. Okay, so when we substitute that and take the integration inside, so integration is also with respect to time, and derivative is also with respect to time. So what happens is that derivative will get cancelled, and you apply the integration by parts, and you see that, and when you apply the limits, it will be e raised to minus infinity is 0, and then minus. Next one is e raised to 0. E raised to 0 is actually 1, and then we are substituting instead of t, so that will be x of 0 or 0 minus. So that will be 0 minus x of 0 minus plus s, then x into integration from 0 to infinity x of t e raised to minus st dt, because we have taken that minus s outside, so that minus and minus gets cancelled and s is coming outside. Okay, so that what is x of 0 minus. What is x of 0 minus? X of 0 minus is nothing but the initial. I told that it's the initial value. So initial value means that is it has taken account the values. It has taken account all the cumulative values from minus infinity to time t is equal to 0. So initial value is the value at time t is equal to 0. So what will be the value of a function at time t is equal to 0? It will be the value accumulated from minus infinity to time t is equal to 0. So x of 0 minus means that is equal to integration from minus infinity to 0 x of t dt. That is inference. So that is why we did not consider integration of in definition of Laplace transform. We didn't consider the integration from minus infinity to infinity. Rather, we considered from 0 to plus infinity, because from minus infinity to 0 is accounted or taken care by x of 0 minus. So that is a proof of that. And this is a very important result. And if that is, if you want to find the Laplace transform of the second order derivative of x of t, what is it? Then d square by dt square of x of t can be written as d by dt x of t. You can write it that. Okay, that means the Laplace transform of such a signal will be equal to Laplace transform of d by dt of x of t. Okay, so we have a signal d by dt of x of t, for which we have to find the derivative. Again, we have to find the derivative, and for that we have to find the Laplace transform. Okay, so we can apply the result of that is we can apply the derivative property. That is here the signal is taken. That is initially when we derive the derivative property, that is d by dt of x of t. Here you can take that d by dt of here we can take the x of t as d by dt of x of t, and for that we are taking the derivative, and for that we are finding the Laplace transform. So we apply the derivative property, and we see that it is s into Laplace transform of dx by dt minus dx of x naught x of 0 by dt. Okay, because that is the initial value. Okay, then we apply the result of Laplace transform of dx by dt, and that is there. That is s into x of s minus x of minus 0 minus d by dt of x of 0 minus. Okay, I hope that is very clear, because we are applying the previous result here. Because instead of x of t, here we have what? Here we have the signal as d by dt of x of t. Okay, and then we apply the derivative property. So that is what we are doing here, and we apply the previous result there, and we open the bracket. That is x square into x of s minus s into x of 0 minus d by dt of x of 0 minus. So the Laplace transform of such a signal is s square x of s minus s into x into x of 0 minus dx of 0 minus by dt, where d by dt of x of 0 minus is the derivative of x of t evaluated at t minus t is equal to 0. So what is x of 0 minus? You have x of t, you apply t is equal to 0, you'll get x of 0 minus, then find the first order derivative, and that is what is d by dt of x of 0 minus. So if that is a result, there can be an inference from that. Similarly, if you have to find the Laplace transform of an nth order derivative, these are extreme cases, but you have to just understand that you have such a result, that is xn of x of s minus s of n minus 1 x of 0 minus x of n minus 2, the first derivative of x of naught, likewise minus of minus until the nth minus 1 derivative, that is already 1 is over, that is 0 is taken care by d raised to 0 by dt raised to 0 is taken care by s raised to n minus 1 x of 0 minus term. That is why the final derivative term is d raised to n minus 1 by dt raised to n minus 1 x of 0 minus. So that is another inference from that property. Similarly, what is a transform of an integral property? That is, if x of t leads to x of s, we have another dummy variable here, that is we are finding the integration from minus infinity to t, that is the present time, x of tau d tau. If you find the Laplace transform, that will be x of s by s plus integration from minus infinity to 0 x of tau d tau by s. So integration from minus infinity to 0 actually indicates the initial value. Okay, that is the value at t is equal to 0. Now we consider, we move to the proof that a little bit, we start with an assumption, that is, let f of t is equal to integration from minus infinity to t x of tau d tau. Then d by dt of x of t is nothing but, okay, that is f of t is nothing but if that integration, then what will be d by dt of f of t? That will be equal to x of t. What is x of t? X of t is nothing but that in the integration. Okay, that integration. So further, f naught of 0 is nothing but, what is f naught of 0? F naught of 0 is nothing but integration from minus infinity to 0 x of tau d tau. Okay, okay, I made a mistake there in the previous step. If we find the derivative of x of t, we'll get that is we get x of t. Okay, that is what. Okay, that is we can write it as x of tau or x of tau or x of t. We have replaced x of tau simply by t because x of tau was a dummy variable. Okay, now f of 0 minus is nothing but the initial value, that is integration from minus infinity to 0 x of tau d tau. That is the value accumulated from minus infinity to 0 time t is equal to 0. Okay, then Laplace transform of such a derivative, that is Laplace transform of d by dt of f of t is nothing but L of x of naught, and that is nothing but, okay, we apply the derivative property, that is s into f of s minus f of 0 minus is equal to x of s. From that f of s is equal to x of s by s plus f of 0 minus by s. Okay, so what is f of 0 minus? F of 0 minus is nothing but integration from minus infinity to 0 x of tau d tau. By s is already there. Okay, you can take that outside, you'll get the final result. So these two results are very important. Okay, because when we solve the differential equation, these two, at least the results are very important, if not the derivative, the proof of that. Then differentiation in S domain. So in the previous step, previous property we have that is in the fourth property, we have found the differentiation in time domain. So what happens if you do the differentiation in S domain, that is in the frequency domain? Then you can see that if you, that is minus d by df, that is t x of t. If we find the Laplace transform, it is equivalent to minus d by ds of x of s. Okay, that is derivative of x of s is nothing but, with respect to s, is nothing but minus t x of t. Okay, so that is another important result. From that, there is a corollary, actually, t raised to n. This is a very important result which you can apply in problems. T raised to n, if you find the Laplace transform of t raised to n, that is nothing but n factorial by s raised to n plus 1. I hope you have seen these results in +2 classes, okay, or in the preliminary engineering mathematics. Okay, then frequency shift property, that is, we have seen what happens when we shift in time domain and what is happening when we shift in frequency. Okay, that is, if x of t Laplace transform leads to x of s, then e raised to minus at x of t will lead to x of s plus a. So that's a very important result. So if you shift s by plus a, then correspondingly what is happening in time domain is that x of t is being multiplied with e raised to minus at. Okay, similarly, e raised to at x of t is nothing but Laplace transform is x of s minus a. Okay, so if you delay s by a, then it is nothing but, in time domain it is x of t multiplied by e raised to at. Then similar to the what we discussed in Fourier transform, convolution property is another important property. That is, if you want to find convolution of two signals in time domain, it is nothing but, and if you find the Laplace transform, then that is nothing but its product of its Fourier transform, product of its Laplace transform individually in frequency domain. That is, x1 of t convolved with x2 of t, Laplace transform is nothing but x1 of s, simply the product of x1 of s and x2 of s. So it's very easy to find. I have some problems also in the later stages. That is, if you want to find the convolution in time domain, simply find individually the Laplace transform, find the product, you'll get a function, a rational function. Then you find the inverse Laplace transform, you'll get the convolved signal. That's very easy to find. Okay, then the ninth property. So in the eighth property, it was simply the convolution in time domain. So convolution can be in frequency domain also. So that is explained by the modulation or convolution in S domain property. That is, then that will be simply the product in time domain. So if you find the product of two signals in time domain, that is x1 of t multiplied with x2 of t, finding the Laplace transform, will get 1 by 2 pi j x1 of s convolved with x2 of s. Then conjugatum property is very simple. That is, if you find the Laplace transform of x star of t, where x star of t is nothing but the complex conjugate of x of t, then its Laplace transform will be x star of x star. Okay. Then another two very important two results, that is initial value theorem and final value theorem. That is, if you want to find what is the value of a signal at t is equal to 0, or if you want to find what is the value of a signal x of t at t is equal to infinity, then these two theorems are very useful. You can simply apply and find the initial and final values of a signal. Okay, so if x of t leads to x of s, then x of t when limit t tends to 0 is nothing but x of 0. X of 0 is nothing but the initial value, that is equal to limit s tends to infinity s into x of s. That is what is initial value theorem. The result is very important, but we'll apply these results in problems coming down under. And final value, that is if x of t Laplace transform leads to x of s, then limit t tends to infinity x of t, that is nothing but x at x of infinity. X of infinity is nothing but the value of the signal at t is equal to infinity. That is a final value of the signal that we can find by finding limit s tends to 0 s into x of s. Okay, so we'll see some of the applications of those two theorems. Determine the initial value, that is x of 0 plus for the following Laplace transform. So we have Laplace transform given by x of s is equal to 4 by s square plus 3s minus 5. So according to initial value theorem, x of 0 plus is nothing but limit s tends to infinity s of x of s, limit that is equal to limit s tends to infinity, that is we have to multiply s with x of s. X of s is nothing but 4 by s square plus 3s minus 5, and here s is not getting cancelled in that cases because there is no term like s in the denominator. So in such cases you have to consider another substitution, that is s is equal to 1 by x. So that is s is equal to 1 by x means, so if s tends to infinity, then surely x tends to 0. 1 by 0 is infinity. That is why when s tends to infinity, x will tend to 0. So if we apply instead of s as 1 by x and put x tends to 0, then you can see that you'll get as limit x tends to 0 for x by 1 plus 3x minus 5x square, that is equal to 0. In the same way, you can see the second problem, which is specified as question number B. There also you can substitute s as minus x where x tends to 0, and if you find that its value is 0, then you can find x of infinity. That is, in the previous two problems we have found the initial value. So what was the initial values of those two problems, those two signals? It was 0. So likewise we can find the final value also, that is 1 by s minus 4. Okay, so I hope you have learned in control systems that what the significance of a pole. What is a pole? The denominator, if you k to 0, you'll get the poles. If you solve the denominator polynomial, then the roots of that denominator polynomial will be the poles. So the position of poles are very important. That is, you have the s plane. What is s plane? That is what I have drawn up just above that page. That is sigma along the x-axis and j omega about the y-axis. Why it is sigma and j omega? Because sigma plus j omega is nothing but our s. So that complete plane is called the s plane. Okay, so a point in s plane will be what? It will be a converging point, or intersection of sigma and j omega points, that j omega axis. So that is why it is called s plane. So each point in s plane is very crucial, and position of poles in that s plane is very, very important. So here you can see that the pole is at s is equal to 4. So that is, the pole is at the right half of the s plane. If the pole is at the right half, then definitely the system is unstable. For an unstable system, you cannot apply the final value theorem. That's a conclusion. That is why I have purposefully put that problem. Then x of s is equal to s minus 2 into s into s plus 4. Here you can see that the poles are, one is at s is equal to 0 and the other is at s is equal to minus 4. So that is, a system is a marginally stable system. Why it's called a marginally stable system? Because we have, we have one pole that is at the origin. Okay, so anytime you cannot work with a marginally stable system, because anytime this pole can, with any other influence of an external factor, this pole can fold to the right half. Okay, so so we can apply here. So what is x of infinity? That is limit s tends to 0, s into x of s. We apply, instead of x of s and s gets cancelled. We apply the value for s is equal to 0 there. So what happens? It is nothing but minus 2 by 4, that is 1 by 2. Now we are moving to the inverse Laplace transform, very important topic in the module. That is, we have learned the equation and another integral for inverse Laplace transform, that is x of t is equal to 1 by 2 pi j integration from minus infinity to infinity x of s e raised to st ds. But thing is that if we apply such an integration, that's a very complex integration, contour integration. So why should we complicate things? We usually find the inverse Laplace transform by a simple technique called partial fraction expansion method. So partial fraction method expansion can be applied for a proper rational function. So by what I mean by the proper rational function is that the order of the denominator should be always greater than the order of the numerator polynomial. That is, if you can see, that is x of s is, it is ns by n of s by d of s. That is a numerator polynomial in s divided by a denominator polynomial in s. You can see that the order of the numerator polynomial is m and order of the denominator polynomial is n. And for a proper rational function, always m should be less than n. So we come across, many times we often come across proper rational functions. So we concentrate in this course proper rational functions, and for proper rational functions we can apply partial fraction expansion method. And if at all it's not a, if that is not a proper rational function, we have to make it a proper rational function. I have an example also regarding that. Okay, so the denominator polynomial is very important. The solution of the denominator is very important, because that will determine whether the system is stable or not. So in the beginning itself, I told that if you solve that denominator polynomial, you can see that the roots are nothing but poles. So if it is an nth order polynomial, then you can expect n roots. So that is why I can write it as s minus p1 into s minus p2 into likewise the last term will be s minus pn, where pn is the last or the nth root. Totally there are n roots. So in order to you can write in a compact way, that is the continued product of s minus pk from k is equal to 1 to n. What is continued product? S minus p1 into s minus p2. That is called continued product. So you can write that in the short form, where pk are the poles. So totally how many pk's are there? N number of pk's are there. So, or n number of poles are there. Now these poles can have different natures. That is, they can be distinct, or each poles will be different, or the second one is multiple poles. Some poles can be repeated, and the third is poles can even be complex also. So if poles are distinct, then you can write the partial fraction expansion as x of s is equal to k1 by s minus p1 plus k2 into s minus p2 up to ki s minus p1 plus kn by s minus pn, where s minus pi are the is the ith root, and the residue of that is ki. That ki, or the k1, k2, ki, kn, all these residues we have to find. So how do we find that? So each one of that has to be found out. Then that can be found out by, that is you can see, that is to determine ki, multiply both sides by s minus p1 and then put s is equal to pi. So you can see that in the above expression, you can of both sides you have to multiply by s minus pi, and then you have to apply s is equal to pi. Then you can see that all other terms other than the term of pi, that is ki, disappear. So what we get is that it is nothing but ki is equal to x of s multiplied by s minus pi, at s is equal to pi. You can find ki's. Likewise, you can find every residues there. And if it is multiple poles, you can see that x of s is equal to k1 by s minus p1 plus k2 by s minus p2 plus ki1 by s minus pi plus ki2 by s minus pi the whole square. You can see that pi is repeated there. Then you can have ki into kil divided by s minus pi raised to l. There the pi'th pole is repeated l number of times. These are very general terms, so be careful about these ones. These are very simple, but when you see the general forms, you might get scared, but there is no need to worry. So what is KIL? How first we have to find what is KIL. What is KIL? You just follow the steps we have explained just earlier. That is, multiply both sides the function by x minus s minus pi the whole raised to l. That is, and then put s is equal to pi there. So x of s being multiplied with s minus pi the whole raised to l, then you substitute s is equal to pi there. You can find the value of KIL. So pi is the pole repeated. You have other pi's also which has residues ki2 and ki1. So how do you find that? So KIL minus 1. So l minus 1 will be ki2 here. So that will be d by ds of s minus pi the whole raised to l x of s at s minus pi. That is, you have to multiply with x of s minus pi the whole raised to l. Then you have to find the derivative with respect to s. Then you have to apply s is equal to pi. I can repeat, that is x of s being multiplied with s minus pi the whole raised to l. Then you find the first derivative of with respect to s, that is d by ds. And after finding the derivative, first order derivative with respect to s, you apply s is equal to pi. Likewise, you can find the next one also. Here the next term will be ki into l minus 2. Ki into l minus 2 will be ki1. So in generally you can write it as ki l minus b is equal to 1 by b factorial. 1 by b factorial. Then inside the bracket, the other things, that is d raised to b by ds raised to b, s minus pi the whole raised to l x of s. Then you have to substitute the value for s as pi. So what you have to do is that x of s is being multiplied with s minus pi the whole raised to l. You find the bth order derivative with respect to s, and then you have to apply s is equal to pi. Then you have to apply multiply the whole thing by 1 by b factorial. Okay, I repeat, x of s is being multiplied by s minus pi the whole raised to l. Then you take the bth order derivative with respect to s. Then you apply s is equal to pi, and then you multiply the whole thing by 1 by b factorial. Okay, then the roots can be complex also. That is, x of s is equal to k1 by s minus p1 plus k1 star by s minus p1 star. Okay, and that there also you can actually follow the same procedures. You can find out that where k1 is the complex conjugate of k1 star is a complex conjugate of k1, and p1 star is a complex conjugate of p1. Okay, so we'll do some problems. That is first one by, and one more thing before going into the problems. That is, see, we have found some important results in Laplace transform. That is under the heading Laplace transform certain unilateral signals. Okay, there we have found certain signals like Laplace transforms of delta of t, then 1 t, tu of t, and then u of t, t square u of t, then e raised to minus at u of t, e raised to at u of t, e raised to minus at cos t u of t, then e raised to at cos t u of t, then e raised to minus at sin t u of t, e raised to at sin t u of t. All those results are very important. I told in that class itself, these results are very important than their derivations. Those results have to be by hearted. You have to keep that in mind, because even if we have learned the partial fraction method, when you see a question, first you have to see first you have to check is that whether that Laplace transform is in any form of that standard signals. Okay, you know what is the Laplace transform of u of t. What is the Laplace transform of u of t? It is 1 by s. So if you see a term in terms of 1 by s, you can straight away write the inverse Laplace transform. No need to have find the residues and find the Laplace partial fraction expansion, not like that. Then if it is e raised to minus at u of t, straight away you know that is 1 by s plus a. So if you find something in such a case, then such a form, then you can actually apply that straight away. So knowing, if you see any Laplace transform in any of the forms that we have seen in the earlier video, straight away you can write the equations. Okay, no need to go and expand using the partial fraction expansion. And if at all you cannot apply, if at all you cannot see anything like the forms we have learned in the previous class, or the forms we have seen under the heading of Laplace transform of unilateral transforms, unilateral signals, then you can apply the partial fraction expansion. Then only you have to apply the partial fraction expansion. Okay, so first question, 1 by s plus 1 the whole square, where, and one more thing, inverse Laplace transform should be accompanied when you have a question to find the inverse Laplace transform, you will be given with the Laplace transform x of s, and that Laplace transform will be accompanied by the ROC. If you don't find the ROC, if you don't see the ROC in the question, that cannot be solved. That is one thing. Okay, so ROC should be accompanied with the Laplace transform. Okay, and when we found the Laplace transform of many signals, we have written the Laplace transform as well as the region of convergence. So region of convergence is very important. That should be accompanied with the Laplace transform, without which you cannot find the inverse Laplace transform. So even if in the university question, if you don't find the region of convergence along with x of s, then you cannot solve the problem. That's very simple. Okay, so here the real part of s should be is given as greater than minus 1. Okay, so just see whether this is in any form. This is a form. What is the form of that? It is in the form of e raised to minus at t u of t. Okay, so otherwise also it is in the, suppose if it is in the form of t u of t. So what is the Laplace transform of t u of t? It is nothing but 1 by s square. Okay, and in addition you have, instead of s, you have s plus a. So s plus a comes when there is e raised to minus at term in the time domain. So that way also you can solve. So that is nothing but, you can write it as e raised to minus a, here it is 1, e raised to minus t, then Laplace inverse of 1 by s square, that is nothing but e raised to minus t ut, or t e raised to minus t u of t. Okay, and then next one, x of s is equal to 1 by s plus 1 the whole square plus 1. Okay, again you can see that it is in the form of 1 square by s square plus 1 square. Okay, instead of s you have s plus a. So s plus a can be accounted by e raised to here it is s plus 1 here. So in s plus 1 can be accounted by writing e raised to minus t. Then remaining will be the Laplace inverse of 1 by s square plus 1 square. That is nothing but what? That is nothing but sine t u of t. So that's the equation. Likewise, the C question, that is x of s is equal to s by s plus 2 the whole square, where region of convergence is greater than minus 2. Then that is, you can write, you have to split the numerator. These are techniques we usually use. That is adding 2 and subtracting 2 from the numerator and splitting that. Then you can get it as, that is it is nothing but Laplace. So s plus 2 and s plus 2 gets cancelled. The remaining will be 1 by s plus 2 minus 2 by s plus 2 the whole square. So that is 2 also can be taken outside. If you find the Laplace transform, s plus 2 can be accounted by e raised to minus 2t. Remaining is Laplace inverse of 1 by s. 1 by s is nothing but what? U of t. So then 2 can be taken outside. Remaining will be 1 by s plus 2 the whole square. S plus 2 can be accounted by e raised to minus 2t. So we other thing is the Laplace inverse of 1 by s square. So accounting all these things, that is u of minus 2t, which accounts for s plus 2, and then 1 by s inverse is u of t minus 2. S plus 2 is accounted by e raised to minus 2t. Then 1 by s square is accounted by t into u of t. So that's all. Then similarly, find the inverse Laplace transform of the following, that is s plus 1 into divided by s plus 1 the whole square plus 4 or 2 square, that is real part of s is greater than minus 1. So that is, here we have, that is in the form of s by s square plus omega square, where omega is 2 here, and s is replaced by simply s plus 1. So s plus 1 can be accounted in time domain as e raised to minus t. Then you have to only find the Laplace inverse of s by s square plus 2 square. So s by s square plus 2 square is nothing but what? Cos 2t u of t. That's all. Then you have the second question, that is s cube plus 1 by s into s plus 1 into s plus 2. Here you can see that this is a case where it is not a proper rational function, because the order of the numerator is same as the order of the denominator. So in that case, you have to expand that denominator and divide that. You have to perform the division, that is s3 plus 1. That is, we have to divide s3 plus 1 by s3 plus 3s square plus 2s, and you get the result. Just find the first division, that is, you'll get the result as minus 3s square minus 2s plus 1. Then you can write the whole thing as 1 minus, because 1 is a numerator. 1, why there is minus? Because we have taken minus sign common from the remainder. That is why it is a minus. Actually, it is 1 plus minus 3s square minus 2s plus 1 divided by the divisor, that is s cube plus 3s square plus 2s. Okay, so when you take the minus outside, it becomes plus, becomes minus sign. Okay, then you can see that I told in the beginning itself, if it is not a rational function, you have to make it a rational function. Now I have made it as a rational function, a constant minus a rational function. Why it is called a rational function? Why it became a rational number now, function now? Because the order of the numerator is now less than the order of the denominator. So we may have made it a rational function. Then you apply, that is, we know the expansion of s3 plus 3s square plus 2s. That is, if you take s outside, that becomes s square plus 3s plus 2. We can expand that, and we can write it as a by s plus b by s plus 1 plus c by s plus 2. And I have applied they are all distinct root. Because why it is called distinct root? Because one is s is equal to 0, the other is s is equal to minus 1, the other is s equal to minus 2. All are distinct roots, and you can apply, you can find s. How can you find s? How can you find the residue a? That is x of s, which is the LHS, is being multiplied by s. That is, the pole is being multiplied. What is the pole there? S minus 0 is the pole there. That s minus 0 is being multiplied with x of s. What is x of s? X of s is nothing but 3s square plus 2s minus 1, the whole divided by s into s plus 1 into s plus 2 and then you have to apply at s is equal to 0. When you apply s is equal to 0, and there you can see s and s gets cancelled, then you have to apply s is equal to 0. The result is minus half. Similarly, you can find the value for b. How can you find the value for b? That is x of s, that is 3s square plus 2s minus 1 by s into s plus 1 into s plus 2 is being multiplied by s plus 1, and then you apply s is equal to minus 1. You get it as 0. Similarly, you can find the value for c. You apply everything, that is minus half by s plus 7 by 2 by s plus 2. So minus half will come outside. Laplace inverse of 1 by s is u of t. Then 7 plus 2 will come outside. 1 by s plus 2 is nothing but s plus 2 is accounted by e raised to minus 2t. Then Laplace inverse of 1 by s is nothing but u of t. Okay. Similarly, you can find the case of the third question also. There you can see that the first s square plus 3s plus 2 can be easily resolved into s plus 1 into s plus 2. Then the s square plus 2s plus y, you cannot do that straight away, but you can do a certain adjustment there. That is, it can be written as cs plus d by s square plus 2s plus 5, because I told that the residue, when you substitute the residue also, that should be a rational function. So you can see that the numerator numerator polynomial order is 1 and the denominator polynomial order is 2. That is cs plus d, the order is 1, s square plus 2s plus 5, the order is 2. Then you can split that, that is equal to a by s plus 1 plus b by s plus 2 plus cs by then S square plus 2s plus 5 can be written as s plus 1 the whole square plus 4. So that can be written as SCS by s square plus 1 the whole square plus 4 plus d by s square plus 1 s square plus 1 the whole square plus 4. Okay, then easily you can find the residues A, B, C and D, and you can substitute that. You can see that it is 2 into e raised to minus t u of t plus 13 by 5 e raised to minus 2t u of t minus 79 by 15. What is it? It is nothing but that is s plus 1 can be replaced by e raised to minus t. It is cos t u of t minus 19 by 3 e raised to minus t sine t u of t. That is it. Okay. Then you can similarly solve the questions also here. Okay. This is the fourth question, is the application of repeated roots. There you can see that s plus 1 repeats again. Okay. So that for that a can be found in the same way as we have discussed here. That is x of s being multiplied by s of s plus 3, and then you substitute s is equal to 3. S equal to minus 3, you get the value for 1. Then straight away go and find C. So what is C? Just like the similar earlier method, you can multiply s plus x of s by s plus 1 the whole square, and then you substitute s is equal to minus 1, you get C is equal to 1. Then you go and find B. B is nothing but, I hope you remember the general equation, that is 1 by b factorial, the bth derivative of s plus pi the whole square, s minus pi the whole raised to L x of s at s is equal to pi. So that equation we will substitute. Here there is only one. If you substitute that is why it is 1 factorial, because L minus b, here there is only b to be found out, that so that is L minus 1, that is that is earlier it was 2 minus 1 is 1, so b is 1 here, so 2 minus 1 is 1, so 1 by 1 factorial, 1 by 1 factorial is 1 itself. D by ds, b is 1, so d by ds s plus 1 the whole square, that is earlier it was x minus p I the whole raised to L, instead we have s plus 1 the whole square. L is equal to 2 here, x of s at s is equal to minus 1. So you have to find we have to substitute the value for x of s, multiply with s plus 1 the whole square, then you have s square plus 3s plus 4 into s plus 3, then you find the derivative with respect to s. After finding the derivative, that is s plus what is the derivative, that is s plus 3 into 2s plus 3 minus s square plus 3s plus 4 into 1 divided by s plus 3 the whole square, and then you substitute the value for s is equal to minus 1. You can see that b is equal to 0. Easily you can find. Then the last question, that is convolution. I told that convolution in time domain can be easily found using a Laplace transform. Simply you have to find the Laplace transform of x1 of t and x2 of t, and then you find the product yield. Okay, so what is the Laplace transform of x1 of t? That is x1 of x is equal to 1 by s plus 2. Then Laplace transform of x2 of 2 is nothing but, so if I delay a signal in time domain, what is correspondingly happening? That was a second property. I stressed on that property. That is nothing but e raised to minus 3s, where 3 is the delayed time, minus 3s by s, e raised to minus 3s multiplied by x of s. What is x of s? That is x of s is nothing but the Laplace transform of x of t. What is x of t? Here it is u of t. So the u of t Laplace transform is 1 by s. Okay, so that is being multiplied. You get it as e raised to minus 3s by s into s plus 2. So when you want to find the convolution in time domain, if you want to find the Laplace transform of two signal convolved in time domain, you simply find the product in frequency domain. That is what I have found. Then if you want to find the convolution, if you want to convert that in the time domain, then you have to find the inverse Laplace transform. Okay, so e raised to minus 3s corresponds to t is equal to t minus 3. So it's, you simply take out that e raised to minus, you simply neglect that e raised to minus 3s, because after finding the inverse Laplace transform, you can simply replace t by t minus 3. That problem will be solved, because e raised to minus 3s is because of t minus 3. if I consider simply, if I neglect that e raised to minus 3s, find the inverse Laplace transform as usual, you'll get a result in result in t. Then after all, you have to substitute t is equal to t minus 3. That is all. So that is what we have doing here. You simply ignore e raised to minus 3s. Why we are ignoring e raised to? We are not simply ignoring e raised to minus 3s, because we are considering e raised to minus 3s, or we are accounting e raised to minus 3s in time domain in the final step by replacing t by t minus 3. So if you simply ignore e raised to minus 3s now, then you can see that it is Laplace inverse of 1 by s into s plus 2 at t is equal to t minus 3. So at t is equal to t minus 3 accounts for e raised to minus 3s. Then as usual, you can find the partial fraction expansion, and you can find a and b. I have not done here because purposefully, because you can find it. A will be half and b will be minus half. Then if you find the inverse Laplace transform, it will be, I just consider this as a temporary result, that is y1 by y1 of t, that is half u of t minus half e raised to minus 2t u of t. So what will be the final result? This inverse Laplace transform should be replaced, that t should be in that t should be replaced by t minus 3. If we substitute t is equal to t minus 3, we get the last result. That is the convolution of those two signals in time domain. So these are the things I want to cover in this majority of the module, and in the next video we will see the solution of differential equations using Laplace transform. Very simple and very important as well. You might have learned in the third semester regarding the differential equations. One subject itself was there in mathematics. So here we'll see very easily how can you solve a differential equation using Laplace transform. So that will be in the next video. Thank you for the patient listening. Thank you.